Is anybody having internet connection in your hometown or in your place where you are joining? If you have, those who have internet connection, I will actually upload it to YouTube later. All our sessions, including tutorials. Okay. So I'm at the moment I'm just having a bit of problem. I do not want to make the YouTube public, so I want it to be a closed group. So I'm doing the setting. If any one of you is having internet problem for the online classes, I will actually upload the sessions into YouTube. So I hope that will actually help all of you. But in any case, if you guys still have problem, please send me an email. See how I can actually assist you guys. Okay. Okay, we are good. We have 15 attendees. Not bad. Hi, Suhas. Good afternoon. I think the participants is increasing and dropping, increasing and dropping. I think something wrong with you guys' internet, but rest assured, I'll upload everything on YouTube, so you guys can actually do some reference later. Okay. Okay. I think I'll start off the lab sessions before I explain on the start on the actual lectures this week. I just want to give a bit of a briefing. I will actually prepare the tutorial I'm preparing, and it will be a PDF. I'll upload the tutorials. What I need you guys to do is just go without actually looking at the answers. Attempt it yourself. Okay, attempt it yourself and see whether you can do or not. The first tutorial will be more on reflective. Reflect back on whatever that you guys have learned. This foundation of digital design would be a good place to start. Okay, whatever that you guys have learned so far, addition, how to do addition, and the logic operators, addition, logic math operations. So I need you guys to actually go through these operations. That will be more on the tutorial, number one. And I will upload the PDF in once I'm done. Just give me, I want to make it nice. So by today, I will upload, okay, the PDF. And as for the lab, I think I sent you guys a Moodle. The lab we conduct in Malaysia will be slightly different from the Benvi counterpart. In Malaysia, we are actually doing using a remote desktop system where you can actually log in to the lab PC at ME102. You don't have to be physically there, and you can actually access the equipment that we have actually plugged into that particular PC. Okay, so all these kind of things we will actually try out a few days, starting from tomorrow. The lecturers, Dr. Philbert and me, we will actually try out first before we let you guys access to it. See if there's any problem. I plan to have 2 workstations for this lab equipment, so all of you will have a session. Let's say, for example, Benson. Okay, Benson, your session will be 8 o'clock to 10 o'clock. Okay, so you will do whatever that you need. Okay, if you can't complete it, it's okay. Send us an email or whatever. You're having problem with this, or the computer is down or whatever. Please send us an email. I will actually help you guys to restart or whatever. Someone has actually requested a WhatsApp group. I feel that this one I'm actually checking with the HOD. See whether it's appropriate or not. Nevertheless, I think we need rapid response for the lab. So I might have something like that. If the PC is down or whatever. For the PC, we can only help. We cannot access the even the lecturers cannot access the campus 24 hours a day. Okay, and we will try our best. If there's problem, you can share with us. Hey, there's a problem. You know, we cannot complete or whatever. Please send us whatever means. I will let you guys know later. Okay, but so I hope that that's for the lectures. Lectures I will upload to YouTube. Tutorials, please attempt first. This week tutorial will be more on the fundamentals. Okay, the logic operators and all these kind of things will be more on the fundamentals. And thirdly is the lab. Okay, and there will be a final exam like what I told you guys. Okay, so a bit of reflection. Last week, if you are with us in this lecture sessions, we've gone through actually the entire. We've gone through actually the entire system, what you'll be learning. I give a brief overview of whatever that you're learning, and a brief overview of whatever a microcontroller or microcomputer is, how to basically differentiate between a microcontroller and a microprocessor. Okay, so a bit of reflection. Okay, in a microprocessor, it's similar to your computer. And hold on. Yes, Philbert, it's not showing at the moment because I haven't started the lectures. In a short while, I will show. Just a recap on whatever that we spoke of. So last week we've talked about the the overview, CPU and all these kind of things. What's important, what we will be studying the whole entire semesters. Bear in mind, this unit it's basically an entry level for microcomputers. So I do not expect at the end of the unit you'll be able to design your own microcontroller model and to sell it on the internet. No, but you'll be having a bit of you have a certain degree of knowledge how this microcomputer works, and what's a CPU, you know, how does it relate to memory and all these kind of things. You excuse me for a moment. Hold on. Okay. So it's a very introductory unit to give you an overview how this microcontrollers and all these kind of things how they function. It's an overview. Okay. So we will let you guys have a bit of hands-on experience in the lab. So at the end of this unit, you should be able to have a big picture. Okay, what do they do? You know, companies that design microcontrollers or companies that design microprocessors. If you go to entry level, you go to a company that actually produces processors, you would actually appreciate whatever that we are learning. So last week also we talked about the a lot of the things. Basically last week we covered the whole entire unit, what you guys will be learning and so on and so forth. So what we're going to do for these subsequent weeks is that we're going to dissect one element by one element that we've discussed last week. Okay, so if you remember, last week we've discussed about CPU, one of it is CPU. We've also discussed about the memory system. The reason I'm always actually checking my WhatsApp is because Dr. Filbert is communicating with me. Okay, I think it should be okay. So he's actually viewing if, let's say, anything is wrong with the screen, he will let me know. That's why I'm always checking. Today's lecture will mostly be about the CPU only. And when we learn about CPU, we are basically, for this lecture, we're going to look at block diagrams and see how does the CPU actually function, what do they do, and what is actually inside the CPU. That's actually very important. So we're going to go through all that. We take one element from last week, which is CPU. We're going to discuss in depth about just this CPU this week. Okay, so topics covered in this lecture today will be the controller unit, the entire controller unit. What consists of this controller unit, and We're also going to look into something that you probably have discussed before in your foundation of digital design. You've probably discussed how to build logic units from basic transistors, from flip-flops, and so on and so forth. You have a vague picture. How is this done? If I said, okay, create a summing circuit for me using transistors, you should have no problem actually creating this after you've gone through your foundations of digital design. Last week, we also discussed basic bus interface logic. When we discuss bus, you reflect back, okay, there are how many types of bus are there? Bus systems. How many types of bus systems are there? There are essentially 3 types, okay? One is for the address. Okay, we've discussed this last week. We will cover this more in more in-depth in the subsequent lectures. There is an address bus where it's used to actually send the address, which memory address that you want to do your stuff. Let's say, for example, you have a RAM, random access memory, and you want to access a certain part of the random access memory. Let's say, for example, A1B5. Okay, so what you do is the bus interface actually sends an address to certain of the memory location, and you extract the information through the data bus. So address bus, data bus, and this control bus, 3 types of interface. Okay, so when you go through the subsequent lectures and you see diagrams, bear in mind you can actually apply whatever that we've learned about bus interface. When you see a diagram, you should be able to differentiate, hey, this line is actually for control. This line is actually for the address. This line is actually for the data, so on and so forth. And then also very important is part of the memory. Okay, last week we always talk about memory. Memory is connected to the controller unit. Without the memory, controller unit does not work at all. Yes, it's true. But when we begin to dissect, when we begin to actually go through this unit, we begin to know that memory has actually separated into different components. One single hardware, different components used for the purpose of this microcontroller, okay, or microprocessor. So a section of this memory, random access memory, will be used as registers. So it's very important for us to understand registers, how they work. And in this unit, I think you'll be able to appreciate if you open in lab 3 next week. Okay, just mark this down. In lab 3 next week, once you start compiling and doing stuff on your microcontroller, what you will see is basically 15 or 16 registers. These registers will be used in any program that you write. Let's say, for example, you write a simple program, okay? Let's give an example. You are writing a program that constantly get data from user and do addition, okay? So this data will be used to, registers will be used to store the data temporarily while the ALU does the operation. And after the ALU does the operation, it will actually store the answer in some other place, one of these temporary registers. So we will go more on that. What are registers? What are they for? You know, how to identify them, and each of these lectures, we will cover all these kind of things in depth. Okay, so you might feel that, hey, sir, these units they are a bit overlapping. The reason how we structure this unit is such that initial lectures we will cover the brief picture. Subsequent lectures we will cover each element more in depth. Okay. Okay. Now we've talked about this fairly well, fairly in depth in the previous lectures. CPU is in a microcomputer is usually a microprocessor unit or a core. Okay, so a brief review back what we learned. What's the difference between microcontroller and processor is that in a microcontroller, you have your CPU in the die, and a microcontroller also have their memory inside the die. So when you go to the shop and you say that, hey, I want to buy an Atmel chip, let's say H6 something something something, you give the code, and everything is actually in the chip itself. The external parts, if no, I actually want you guys to actually, everybody has a microcontroller at their home. Most of you are actually second year, you start to play with the microcontrollers, you might be joining IEEE, then you start to have access to all these kind of things. In fact, at your age, some of you might have actually started to play with all these kind of things even in your secondary school. You might have access to Lego Mindstorm, or even they have this thing called, I forgot what's the BBC chip, what's it called? The one that uses Python, I'm not sure what is it called. Then of course you have something that a lot of Malaysian schools they have now introducing. They have this thing called Arduino. A lot of you have access, you know. So if you really have access to this kind of things, you know, it will be useful to just take out and to explore, hey, why are there so many chips? You know, according to Dr. Wong, microcontrollers are not processor. A lot of the Arduinos are actually microcontrollers. You look, hey, according to Dr. Wong, I quote Dr. Wong, he says that microcontroller, you only need one chip to actually make it work, bare minimum, okay? And then you need the crystal, of course you need a clock, okay? Without the clock, instruction doesn't happen because everything is sequential. And you look at the other stuff on the board, okay? You'll find that other stuff on the board are basically for different purposes. Let's say, for example, it's not to make the microcontroller functional. Is more to having additional stuff for that board itself. Let's give an example. Arduino, if you can see, there's 4 or 5 components. It looks very similar like a chip, okay? But these components, the external components, are basically for USB interface, okay? They are for probably power supply and all these kind of things. They are not not to assist the CPU in any way to run the program, okay? So if you look at the Arduino Uno, only that chip itself is required. In fact, some of you can actually take out the chip after you burn the code inside. You can take out the chip, just put a clock for it to work. It will work by itself. All you need is a power supply, a clock, and the chip itself after you program the after you've done your programming into the microcontroller. So why do some people do that? You know, the reason people do that is because that will make the chip interface much smaller. In fact, a lot of us, a lot of the programmers would actually first burn it using the Arduino board, and then they will actually take out the chip. Then they will build another circuit. They call it the bare minimum circuit, so that the footprint will actually be smaller. They can put it in their hand. They can build variables and whatsoever. You don't need the USB anymore after you've actually completed programming. So try to look into, relate with whatever that we've learned. Some of you might have stuff that are spoiled. I'll give you an example. I used to have a washing machine, an automatic washing machine that is spoiled. I'm so curious to actually find out, hey, what is inside that washing machine that makes it work, you know? So I start to rip off, you know, start to explore, is washing machine actually using a microprocessor or microcontroller? What model they're using? Most of this washing machine, they're actually using this fuzzy logic circuits as the core, and then probably they have another microcontroller. Another plus point I want to give to you, another important key point I want to give to you, is that a lot of the microprocessors have the capability to actually run OS. Okay, they have the capability to run OS, and a lot of the microcontroller, however, you need to program it. It doesn't run OS. Okay, I mean generally, not maybe some microcontrollers can run OS. You've heard of people trying to port Linux to your regular Arduino Uno, but it's very slow. Okay, if you look at YouTube, there are thousands of all these kind of websites that they brag about, hey, how we're able to to run Linux, very light Linux on Arduino Uno. That's possible. That's possible. It's not an I'm not saying that it's a blanket case. All the microcontroller cannot run OS. No, it's not that. Okay, but generally, look at it. All the microprocessors are mostly to run OS. All the microcontroller units are to do simple basic stuff. Okay. Okay, so now the CPU, actually, if you look at the CPU, dissect it, it consists of an ALU. Whatever that you learn in your FDD, how do you do, give you a very simple logic, okay, parallel 8 bits, okay, you extract it, and then you plus with another 8 bits, you get the logic. Maybe you have you're given a set of AND gates, okay, design the circuit, give you a bunch of AND gates, design a circuit that make an addition, with addition operation using this AND gates. So you start to configure and all this. Now, all these kind of circuits that you have learned in your foundation of digital design are actually in your in this arithmetic logic unit. Hold on, I'd just like to verify whether I'm actually recording this or not. Yes, I'm actually recording this, no problem. Okay, so whatever that you learn in your FDD, how to build circuits that do addition, that do all these kind of things, addition, logic, XOR, or whatever, these kind of things you can reflect and actually we use this information to actually look into how you design this ALU. Okay, so CPU consists of one of the component is ALU. You can say, since everybody can design an ALU, well, it's no big deal, but it's actually how efficient you design the ALU. Okay, sorry, I just now I forgot. How efficient you design the ALU, how fast, and all these kind of things, the carry bit and all these kind of things. So all these kind of things are basically an art, how you make the ALU work better. Okay, then you have this thing called controller unit. Okay, how you process the information. When I speak about information, this program is not actually referring to the C programming that you type. Let's say, for example, you guys are very good in programming things, let's say blinking LED, all right? So blinking LED, you have a loop, you program it in C, and what your IDE does is that it actually converts whatever C programming language that you've done into a type of instruction set. I've shared with you last week, there are two formats of instruction sets, okay? The first instruction set format is what they call RISC, R-I-S-C. The second instruction set format is what we call CIS, complex instruction set. RISC and CIS, which one normally comes more expensive is of course the complex instruction sets, okay? So this is some questions that can actually ask you, okay, what are the two formats that are available for all the micro computers that are in the market, okay? So you can answer, well, there is two types of format. One is what we call RISC, the other one is what we CIS. So maybe we can have maybe in the tutorials later, we can do a bit of discussion. Okay, is this instruction set, is it a RISC or CIS? But we're not going to ask you, okay, these 10 lines, is it a RISC or a CIS in the exams? It's a bit over, okay? But I expect you guys to actually just read up about it. Then, of course, you have this thing called registers. We're going to cover a bit about registers. Okay, instruction sets. Again, instruction sets, these are the formats that I spoke of, the RISC and CIS formats. Instruction set does not refer to the C programming that you code or whatever. It refers to whatever that you compile, the information that you compile in the in your memory, your random access memory. Okay, and these instructions will give the instructions to how this CPU will run. Let's say, for example, continuously blink the LED left, right, if there's two LED. So the C programming that you write will be converted into a set of instructions, 16-bit, 8-bit, or whatever. The CPU actually extracts this information. When you do a loop, how does a PC, you do a for, let's say, forever loop, while one, blink the LED, and Okay, this is a simple example, and when you compile it, it becomes something else, you know, that's more low-level language. So this instruction set consists of a low-level language. Now, what do I mean by addressing mode? The second CPU software component is these two things are software components that you need to study about the CPU. Okay, the first is the instruction sets. It doesn't refer to the C programming, it refers to the low-level language. Okay, there is a RISC format, then there is a sys format. Now, the addressing mode. Now, what do I mean by addressing? Now, let's say, for example, you have a value in the register number 5, okay, and you have a value in register number 6. Okay, you want to do something to these registers. Now, there is a lot of way how you access the information in the register. When I mean lot of way, I mean coding. Okay, you can use an immediate coding. You can use a direct approach. You can use all this approach. Generally, there are 4 addressing modes. It's basically how you program. Now, immediate, direct, or whatever mode that you choose to use, they will have consequences. They will have effects on the register. Some addressing modes will actually erase whatever value after you get the information or whatever. You know, the certain registers change value after, depending on the addressing modes that you use. Okay, so it's good to be able to use certain addressing mode for certain purpose. Okay, so 2 things: instruction sets and the addressing modes. We will cover more on instruction sets when I do a forever loop. Inside the forever loop, there is a blinking LED. You know, how does it work? You know, how is the information stored in the memory? All those kind of things we will actually explore. Now, this is a minimal architecture component in a simple CPU. You can see that last week we've actually spoke about the bus interface. It seems I've actually oversimplified, okay? But the bus interface actually, the bus actually requires a bus interface logic. It has to be a component built up of logics that able to transport the information from other components to this CPU. Now, this CPU is an integrated block. Now, if I ask you, this looks a bit like this itself is probably the microcontroller, and the external pins you can communicate. I think this is, if I'm not mistaken, this could be a microprocessor. All right. So you have your control unit. Control unit process the instruction sets. Okay, let's give an example of your LED. Forever blinking LED, your while one blink LED, and simple 3-line code in your C programming. So your CPU will extract the first information from your reboot. Okay, go to get the information from this register, process the information, you know, send it to the I/O pins to blink the LED, come back, repeat, you know. So all this information will be stored in the address. Okay, the memory address. The memory address this CPU will send the which address it wants to extract from the memory, and then the information will be from the data bus. Okay, of course you also have the instruction register and all these kind of things. There is a mechanism how this instruction is actually extracted. There is a mechanism we will explore further. Don't worry. Now, all these registers are actually important. These are general purpose register 1, 2, 3, 4, and so on. Normally there is 15. Okay, standard microcontrollers about 15 or 16 microcontrollers. You have this general purpose registers. If you can see, PC and this stack pointer are specific registers. They are not for your programming purpose, but different registers. Here you can see that they are general purpose register. GP means general purpose registers. We're going to explore what this general purpose registers does. But apart from general purpose registers, you have this PC, SP, and all these kind of things which are very important for the functioning of the microcontrollers. Of course, you can see after you process all these instruction sets, what happened is that you need to put it in the ALU. ALU will process. Let's say, for example, you move register 1, register 6 information into register, all this information registers, and you want to do an arithmetic. You do an AND the information in general purpose register 0 and 1. What will happen is that the information will be passed to the ALU. It does all the things, and then it will send back, to the value to the general purpose registers. Okay, so this is just an overview, different block diagram, and probably in a big company next time, if you ever involve in this kind of things, you'll be in charge of probably one small section. Okay. Now, a few of the these are actually key terms when we talk about data path. Okay, it means that the collection of hardware components within the CPU that are to perform the data operation. Means to say that how do I extract the information to and fro? Okay, let's say for example, I want to extract the information from register, from memory to registers and so on and so forth, from the register to the ALU and so on and so forth. Now this term is called data path. How do I move the data around? This includes the ALU, the internal floating hardware, so on and so forth. It talks about how information is moved inside the CPU itself. Okay, so you have information from the general purpose register. How is it actually being moved to the ALU and so on and so forth? This is actually what they call data path. How fast is your information traveling? How do you optimize it? So all this actually requires advanced knowledge in logic design. So, but for us, it's suffice to actually understand the basic concept. Okay, data path. How do you move information around, and hardware multipliers and so on and so forth? How do we make it more optimal? Okay, so generally all the microcontrollers, they function more or less the same way. Data path design is basically more or less the same, but maybe in the future someone can come up with a more optimal solution. Okay, now another term is what we call control path. Okay, so control path is basically how we control the different components in the CPU itself. You can see, how do I make this guy, transfer information to this? There must be some control path. Maybe I can activate this ALU, I can activate this temporary register, and I can activate this some of these components. So which one do I activate in order to make this whole block as a functional microcontroller? It is a term where we collectively call control path. Okay, so similarly, we can relate back with whatever that we've done. Last week I told you guys, there are 3 types of buses: the control, address, and all these kind of things. So we can relate even inside the CPU itself. There is an element called control path. How do we make on and off, each component? If you can see, there are some write and read elements, inside these components itself. So it's not so simple. You need to think about all these components if you are actually to design a microcontroller. So the work of designing a microcontroller, you might be able to purchase a microcontroller, whether it's a PIC 16 or Texas Instrument, NMEL or whatever. It might look that well, it's a very simple device that costs you about 20 to 30 US dollar or whatsoever. It might be a very cheap device, but because it's so cheap, it's because of the economics of scale. You develop something at a very big scale, it becomes very cheap. But in order to develop this thing, it's a very complex process. Okay, and it takes years after years of refining to come up with a very basic microcontroller. So this much we can share with you. Control path means how do I synchronize. Also, we look at this term timing. Okay, so timing is something that's very complicated when you actually delve deeper into this these units. So timing, how do I make all this information when they're traveling around? How do I create timing where information can be passed around effectively and things can be done effectively. So there's only two jargons here regarding the CPU process itself, inside the CPU process, okay? Data path and of course the control path, okay? So these are two jargons. You can read more about it in the ebook that I sent to you. Again, the ebook is a 648 page document. It is more or less like the textbook that we are using for this unit. You can actually download it from the lecture slides folder in Moodle. Okay. Now, generally, we've talked about the CPU. What is inside the CPU? We know that there is an ALU inside the CPU itself, but inside the CPU, there's also a unit called the CU, control unit. Okay, you can see there's a controller unit, and then there is an ALU. These two things do different things. The CU actually process the instructions that you have. ALU does the arithmetic or the logics that you have. So we're going to study these two things, very important. And primary operation in the CU is basically to continuously do these three things. Fetch the instruction, decode the instruction, execute the instruction. So you get the memory probably connected here. What the CPU does is that it extracts the information from the memory, and then whatever information the program sets that you have, it will process. You know, it will fetch, decode, execute, fetch, decode, execute. So it's a very repetitive task, what we call machine repetitive task. It does the thing again and again and again. Okay, so you can imagine that there is actually three states. There's only three states. This controller unit, it only does three things. It fetch, it decodes, and then it executes the instructions stored in your memory. Okay, so these three states are actually what we call the instruction cycles, or the CPU cycle. Okay, so this controller unit, no matter how you design it, how smart, how effective is your controller unit, controller unit does these three things. They fetch, they decode, they execute. Okay. Okay, so if you blow it up, that's how it actually looks like. This is a MIPS diagram. This is a block diagram, and you can see that if you blow it up, you know, it looks something like this. Now get used to these kind of things. The block diagram for marks and all these kind of things, it's time to reflect back. Okay, so these are selectors. Okay, selectors. So these selectors enable the control which mode you want to use, whether it's a read or write. Okay, so if 0 is 1 is read mode, 0 is the write mode, and so on and so forth. Now, as you can see, controller unit has access to data memory. It can actually access whether you want to read or you want to write. Okay, let's say for example, in this CPU cycle, most of the time is you read. So you do a selection. Okay, I want to read the data, I put 1. Okay, this CPU will control this operation. Control path. Okay, I want to, now this is reflect back what we learned just now. Data path, control path. Okay, so these are the control path, how we access memory. Control path. Okay, it gets information and instruction to the controller unit. Control unit decode, you know, what this instruction actually mean, what is there related to which component, and then it does the execution. Now the execution could probably be passed to the ALU. Let's say for example, you have a subtraction operation. You know, it takes an instruction here to the controller unit, and then the controller unit decodes the instruction, and the instruction actually means that you need to extract two values from a register. So it gets two value from the register. Okay, it gets two value from the register, and it passes this information to the ALU to do, and it passes back to the temporary register and off to the external memory. If this is just an example, it could be other instruction sets. So this is how it works. It's always, this guy is always just doing this three repetitive tasks. Fetch the instruction, the instruction, it decodes what is the instruction about. You know, if most of the instructions are actually in hex file. You need to decode. Okay, decode. After I decode is an operation that involves a few registers. So after I decode, I need to do something with the instruction that's execute, then pass back the information to registers or whatsoever. So this is basically what the controller unit does. Okay. So another, this is a state diagram. Okay. You remember FDD? I do not know what you guys learned in FDD, but I have a vague picture. You guys learn a lot about all these kind of fetch cycles. Probably you are familiar. Now bear in mind that in this fetch cycle, now why is the reason that there is this element here reset? Because now sometimes when you have problem with your, let's say for example your PC hang, okay, you have a watchdog timer, it will always go back to the reset address, which is most of the time is 0x something something. Is a defined reset address. Every single microcontroller have a defined reset address. Okay, it starts somewhere. On your PC, it will always start with this reset address. It will first prompt the fetch state. The fetch will go and then forever be in this loop. But what happens if your PC is hang? Now, when your PC is hang, it will go back to your reset address. Then it will start all over again. Now, how does the PC know that we are actually the microcontroller is in a hang state? So there are a lot of mechanisms involved. Like what I said, this little machine is being refined for ages, 40, 50, 60 years. Some of these 8085 microcontroller or microprocessor is still being used in certain components because it's so efficient. Okay, so there is not much stuff that you can actually improve anymore in 8085. It's a very efficient machine. So they've added only over the years, they've probably refined and added a lot of stuff, make it more efficient. But this reset mechanism, it works in such a way. It always starts with the reset address, and then it goes to the fetch, decode, execute, and then it goes on forever and ever until something happens. It jumps back to the reset address. Okay, so it's like a reset address is where the microcontroller or the microprocessor always start from. Okay, that's the first address. That's the first instruction set that the microcontroller will always start from. Okay. Now, I hope that you are familiar with program counter. So this program counter element, every time you process a program, it will count. Okay, so it will count, and this program counter is also involved in all these kind of mechanisms to track if your PC or your microcontroller needs a reboot. Instruction register, okay, it stores the next instruction set to be processed. Very important. We might actually ask ourselves, hey, why do you need so complicated things? Well, all these kind of things has been ongoing debate, and they find that this configuration, this buffer system, is probably the most efficient. There is reasons for it. We ask ourselves, hey, why do you need another buffer to store this instruction? So there's reason for it. Okay. They've been refining this process for a very long time, and they found that, hey, we need a buffer to store the instruction register. We will actually get into this PC and this IR instruction register in a very in-depth. Again, we will go more in-depth on these two elements itself. There is probably a lecture or half a lecture on this. And now, okay, now we discussed, we previously discussed there is a, sorry, where is the, okay, this is a fetch, decode, execute. So we're going to look into fetch. What do we mean by fetch? Fetch instruction. A new instruction is brought over from memory to the CPU using bus interface logic. Okay, look back into this. Look back into this initial diagram. Okay, so this CPU, when it's actually in a fetch state, okay, fetch state from the reset, it goes to the fetch state. From the fetch state, it will try to get the first address. Go inside here, process, send it to ALU, and then go back to the register and so on and so forth. So we're talking about the first state, which is the fetch state. it fetch an instruction from the bus interface logic. The program counter provides the address of the instruction set to be fetched from the memory. So the program counter will always have the instruction set of the next memory, okay, where the instruction set is stored. Okay, let's say for example A1, B1, okay, is the next address where the instruction is stored. So this program memory will contain the instruction set. This is sort of like an exam question. They always ask this mechanism. You know, what is the, if this is the address of the next instruction, what will be the content of the program counter? Okay, so everything is given. You need to know roughly how it works. Okay, this fetch instruction is read along the data bus and stored in the instruction register. Now, instruction register store the instruction itself. Program counter only store the address. So please get these two things very clear. Okay. So in the fetch state, two things are done. You get the PC and you get the instruction into the IR. Now in the second state, if you decode, the CU needs to understand what does this instruction means. Whether it's you need to access the ALU or you need to access whatever, what process in the ALU, all those will be decoded in the decoding state. Okay, so from the fetch state to the decoding state, it will decode and find out what are the resources that you actually need to process this information. And finally, the third state, you will go to the execution. Let's say, for example, move some memory to register 5, okay, and then do some process, okay. So let's say it's an addition process. So the execution state will be done in the probably the arithmetic logic unit, because the controller unit does not do the operation. Okay, the ALU does the operation. And then after the operation is done, you know, it saves the information, the answer back into the registers. Okay, so this is the execution state. It always fetch, decode, execute, and then after the execute, it will go back into to fetch another instruction from the memory. So it goes around and round and round and round until something happens. Your CPU hang, then it goes into the reset. Or the user press the reset pin, it goes into the reset. Okay, and there's another possibility. They call it the brownout. So when the voltage that you supply is below certain threshold, it will also go to the reset address. So there's a couple of things that can actually happen to bring your microcontroller or your microprocessor to the reset state. Okay, so I hope that helps you to actually understand what happens, okay, and why this reset vector is important. Now, reset signal is required to initiate cycle for the first time. Yes, it will, once you on the PC, it will always go into the reset address. From the reset, it will fetch the next instruction. Then it will go through the loop again and again and again until something happens, goes back to the reset. Okay. So the PC is hardwired to load. Okay, it's a hardwired. It's not programmable. It's hardwired to actually do these kind of things. So when you realize, and another example that I like to give you, if you look at your Arduino Uno, now look at the stash of I/O pins in your Arduino Uno. Inside the Arduino Uno, there is a button called Master Reset. Now this Master Reset is connected to 5 volts to one of the master reset pin. When you press it, the reset pin will go to 0. Your whole microcontroller will go back to your reset address. So this reset address is called reset vector. Some books call it reset address or whatever. It actually refers to the same thing, whether you call it a vector or an address. Okay. Okay. Now, arithmetic logic unit consists of 2 parts. Okay, your arithmetic unit and your logic unit. Your arithmetic unit does the AND, OR, XOR, shift, whatever. These are what we call logic operations. You will learn more about this in your assembly language. Okay, there's another type of operators. They call it arithmetic unit, addition, whatever. There's only one operation that's very rare. Some microcontrollers have it. It's actually called multiplication. Now, for you, multiplication, because you're a human, multiplication is a very difficult thing to do in terms of binary. You need some special stuff to do it, or you need to cascade some logics. Not all, if you look at sets, not all the microcontrollers have this multiplier. Okay, so you have addition, subtraction. These are very common. All the microcontrollers have it. Multiplier, no, they don't have it. So you need to have normally for Texas Instrument, they have the built-in hardware type of multiplier. Yes, they have this kind of thing, special thing to attract more people to buy this Texas Instrument microcontroller. Don't know what is this, not important. Okay, so my multiplier is the one that depends on the brand. Some is not in the standard package. Okay, so multiplication is sort of like a difficult thing to do in terms of binary, but it's easy to do for us humans. Okay, the CU governs the ALU by specifying what operations to perform, the source operation and the destination result. So ALU is actually controlled by the controller unit. Yeah, bear in mind we have this thing called control path. Okay, so this CU actually controls the ALU. It sends information, you process it, then you send it back. Okay, so for example, 16-bit is capable of operation. Now this ALU needs to report to this CU. So we have a control path. Okay, how does it actually work? CU gets the register information, sends it to the ALU, and then after the information is completed, sends it back to the controller unit. You can see this, I hope you are familiar with these diagrams. When you see something like this, it means to say that it's a parallel bus, okay, or parallel bits. This means 0 to 3, 4 bits, 4 bits, okay, 4 bits, 4 bits. Now, look at this picture. There is actually two components. One to perform the arithmetic, the other one is to perform the logic. Okay, so I reflect back. If you want to go deeper and deeper now, computers is like this. Okay, it doesn't mean that the more advanced language that you know, the more you know about computers. No, it's the other way around. The more low-level language that you know, the more advanced your level is on computer architecture. Okay, so you're very familiar with C programming, all these kind of things in your first year. Now we go more and more to the hardware level, the more fundamental and low level. Okay, so the low level part is that most of the time we assume that this ALU is just one block diagram, like this. Okay, we see that, wow, ALU is basically just a block. Okay, lo and behold, when we actually open up, it actually consists of two logic units. How do they design logic units? There are a lot of resources on how do you design logic units, arithmetic units based on your cascaded transistors or whatever. Finish, you have this thing called carry. Okay, so when we do all these operations, you always have a carry bit. Okay, let's say you have 16-bit value. Okay, you calculate, you get a value. You always need this carry bit. Okay, if not, answers will not be valid. Can you guys identify the pins that are associated with the controls? Okay, so this CU actually controls whether it wants to do an arithmetic logic operator or logic operator by using this control path. Okay, so as you can see, we can reflect back control path. Okay, S1 and S0 is basically to control whether you want to do an arithmetic unit operator or a logic operator. Okay, and so we can relate. Okay, and basically a lot of you in your foundation of digital design, you always like to extract information like this. Inside, when you click it, you know, it consists of this two block diagram. So that's more on the FPGA side. Okay, but nevertheless, you get the idea. Now, we've talked about how does the CPU actually communicate with the external memories. We simplified last week. We said that, well, there are actually very small wires, you know, that actually it's not that simple. Look back into the diagram, and you can see that there is a specific interface logic associated with this control bus and all these kind of buses. So this this part here is a bunch of logic that enables you to communicate with external memories. So if last week we sort of like simplified the thing, but this week we want to discuss a bit more about bus interface logic. You want to interface with the controller bus, the address bus, or the data bus. Is not as simple as ABC. You need to have an interface logic. Okay, so we will cover this more and more in depth as we go. Registers are basically temporary memories located inside your CPU. Like what I mentioned just now, you have specific purpose registers that are needed for your operation, your fetch, decode, and execute cycle. Okay. Now go back into this. You can see that PC and SP are required for the programming to run the three states. IR also is required. It's a type of register required for your PC to be functional. But GR0, 1, 2, 3, 4, basically these all are general purpose registers that you can store information and perform your operation. So whatever that you extract from your external memory, okay, will be stored here temporarily in order for the ALU to perform. Okay, so there is a interface logic required to interface with the external memory, not as simple as that. Okay, so registers, there are general purpose registers, then there are specific purpose registers. They are volatile, means to say that if you off you pull out the 5 volts connected to the microcontroller, the register value will just disappear. They are what we call volatile. Volatile means power on, it retains the information. Power off, information is gone. Okay, normally if you have a microcontroller, there are a bunch of flip-flops that you can use to actually build these registers. Flip-flops, you power off, the states turn off, gone. Okay, but as long as you have power connected to the flip-flops, you have information inside the flip-flop. Okay, so general purpose registers are basically to do your operations, pointers and so on, the data variables and so on and so forth. Let's look at specific purpose registers. They are instruction register, like what we discussed now. Reflect back, what is the instruction register used for? They are to store temporary, to store the instruction sets temporarily inside the PC, the computer or the CPU. Okay, temporary. Program counter counts. Then you have this thing called stack pointer and state register, which we will cover more and more in depth. These two things are basically used to for memory purpose to save the stack pointers. Means to say that which part of the memory at the moment is actually being used. So there is a pointer, and we call this pointer the stack pointer that points to the stack of the memory. Okay, so I want to be a bit light this week because there's a lot of things to cover, and I want to give you a bit of space to actually absorb all these kind of things, because this is very important. This chapter is actually very important. Look back into this, revisit whatever lectures that we've talked about on this specific units. Bus interface, general purpose registers, the three states doing the things over and over again, fetch, decode, execute. What does the ALU work? What is the data path? What is the control path? So I think that's about it. I just want you guys, we cover quite a bit today. That's why I don't want to rush these parts. And we will reflect on the tutorials, on whatever that we have covered last week and this week, a bit of whatever that we've covered. So I hope that you do a revision. Basically today we've introduced you to the concept of what actually happens in the CPU. Okay, so I think that's about it for this week lecture. Hope that you guys can, any questions that you have, please send me an email. Tutorials will be recorded because everybody will have access to tutorials. I will continue to do live and record for lectures. Okay, labs, we will give more information, but generally I want to tell that we are using a webcam so that you guys will have to open the webcam to see the states in the microcontroller. You don't need an equipment. All you need is
to open the remote access, you have the equipment connected to your remote access desktop. Okay, so I think that's about it for this week. Thank you for attending our lectures. I see you guys soon. Okay, so see you Suhas, Ben, see you guys.